Hello there everyone. Today we are going to talk about a very exciting subject in physics. Okay, you may have wondered where all of this electricity and all of these voltage power supplies are coming from. You guessed, the battery. That's good. The battery uses a chemical reaction. Solar cells, that's another way. But we have been actually feeding off, moving a magnet or a permanent magnet within the vicinity of an electric circuit, make some changes in that circuit that makes it induce an electric current and thus a voltage difference and what we call an electromotive force. We call it an induced electromotive force. How does this happen? Okay, let's look at this circuit here that you see in front of you. In this circuit here, as you can see, there is no batteries at all. This here is an ammeter. An ammeter is reading zero current, and that's okay. That's true for now. This is a closed circuit, and we wrap around like a coil just to show the direction of the current that is going to happen. This is a magnet next to that circuit. Nothing is happening. There's no battery. Magnet is not moving. Okay, and that will induce no current at all. So this is situation number one. A magnet is sitting next to a circuit and no electric current or electromotive force is induced. Now what happens if we go here and move this magnet closer? The action of movement of this, I'm going to move this magnet with a velocity. So this magnet, this is the north side and this is the south side. And we know the magnetic field lines are going like this within the vicinity of the magnet. The action of moving the magnet closer to the circuit makes more magnetic field lines cross that circuit here. Now I'll tell you something, the circuit does not like that because there's going to be a change, an increase of the North Pole's magnetic flux within the vicinity of the circuit. The circuit does not like that. So the circuit comes with its own magnetic field to oppose the change in the original magnetic field. So it makes a magnetic field that is opposing this magnetic field to try to stop it from coming closer. So the north side here will be created for this induced magnetic field and the south side here. Now if you use the second right hand rule, okay, remember this is my left and this is my right. The second right hand rule, such that you grab on the coil in such a way your thumb points to the magnetic field, then you will have a current that goes through this circuit this way and a current will be induced. So basically what happens is that you're getting this magnet closer to the circuit. The circuit does not like that. The way it reacts to it is to make an induced magnet that is opposite to the increasing magnet, the original one here. And the way to do that is to create a current that creates this magnet, and the current is created. If a current is created, this means that the current is moving from one side to another, from a higher potential to a lower potential. Moving a current from a higher potential to a lower potential means what? We have a voltage difference. Voltage difference, what we call sometimes electromotive force. Since this electromotive force is not permanent and it's induced, we call it an induced electromotive force. And that's amazing. That's how we make most of our electricity. Now let's look at another situation here. In this situation here, as you can see, we are also moving the magnet, but the motion is opposite to what the motion was in this one here. So we're moving it away. Okay, so basically we have magnetic field lines that are crossing this circuit, and as we move the magnet away, the amount of magnetic field lines crossing this circuit are getting less and less by the minute or by the second. Again, the circuit here does not like this kind of change. Okay? The way the circuit reacts to it is it tries to grasp on the escaping magnetic field. It tries to make its own magnetic field to grasp on it. So it makes a magnet here that is south, and a magnetic here, the pole here is north and here is south. And the way this south is going to work on the north here, that it's going to try to attract it, to keep it from moving away. And the only way to do that is to make a magnet south here and north here. And if you do that, so basically your current will be, if you grab on it so that your magnetic field direction is this way, towards the north. Remember, this is my right, okay? So the magnetic field will be like this. If that's the case, the only way is we have a magnetic current going this way. As you can see, the magnetic current in this case is opposite to the one in this case. Look, the needle here going to the right, the needle here on this ammeter is going to the left. This means that we created a current that is opposite in direction. Look at this direction here and look at this direction here. They're totally opposite to each other. And that's what really happens. So let's think of my hand as a coil. If there is a magnet here coming closer to the coil, my hand, which represents the circuit or the coil, is going to try to make a magnetic field to slow down the movement towards me. If the magnet is going away, my hand, which represents the coil, is going to make a magnetic field to slow down the change which is moving away. So it's always opposite to the change. Remember that. It's trying to do opposite to the change. And the reason for that is actually conservation of energy. All right. Now, is there another way? Can we have like a coil like this, and then we have a magnet next to it, wherever that is, north or south, or it doesn't matter. And this coil here, or loop, is being moved back and forth within the vicinity of a magnet. Can we use that to make an electric current, an induced electric current, an induced EMF? You bet. Yes, we can do that. So either moving the magnet or moving the coil itself. All right. There is another way actually, is by making this coil bigger and then smaller, like making it vibrate or oscillate between big and small, keeping it connected, of course. Okay, that will also induce an electromotive force within that loop. I think that's it for this one. Thank you.